Hello students, welcome back. Today we're going to be continuing talking about functions, transformations, and composite functions. So let's recall, last lesson we talked about the introduction of functions. So here would be an example graph of a function, right? So the black line represents the function f of x, or y equal to f of x. That's one of our notations. And the height of the function is the f of x value, right? So on the y-axis, f of x represents the y-axis and the height of the function. Meanwhile, x represents the distance, horizontal distance of the function. So last time we were looking at the domains and the range of the function, and here would be a nice graphical representation finding of a domain and the range of some sort of a cubic polynomial. Okay, so we have the domain, right? Let's say we are restricting the interval. So our domain in this case is going to be from -1 to +5. So x belongs to -1 and +5. Okay, and the range is y. The range would be from -3, right? This is -3 to +3. So we would have -3 to +3. Okay, now let's go ahead and move on to the more of the useful of the use of the functions. So how can we actually say which one is a function, which one's not? We gave a definition last time, but sometimes we can't really test it or use it to for sure know what kind of function we have and is it actually a function. So here would be more of an example of how we can actually test it. So we call it the vertical test, right? Or vertical line test. It's a set of points in the coordinate plane is the graph of y as a function of x, if and only if no vertical line intersects the graph at more than one point. Right, so if we draw a vertical line on the xy axis, we can only intersect the f of x only once. Right, this is the key point of vertical test. So here would be some of the interesting drawings from the book. So here we have 3 functions. Right, let's discuss each one of them separately. So we want to draw a vertical line, right? So vertical line, so what do you think for part A? Is that graph, is that f of x, is it a function or not? And the answer would be no. This is not a function. Not a function. Why? Not a function. Because if we do the vertical line test, we're intersecting the f of x here at 2 points. Right, so that is not, that means this solution x, well, this value x, right, which is x equal to 2, the moment we plug that into f of x, we get 2 completely different solutions. We get like 2.5 and -0.5. That cannot happen for a function, so this is not a function. Meanwhile, for part B, right, this is a perfectly valid function. If we draw one line anywhere, vertical line, we're gonna intersect the f of x only once. Right, this is our f of x. So we're gonna intersect it only once, so yes. It is a function. It is a function. Okay, and same thing for C. Even though we have a gap here, that's because we could say, well, we could restrict the interval, right? We can restrict the domain. We can restrict the domain, so the domain is restricted such that we have this kind of graph, and it will pass the vertical line test. So once again, yes, it is a function. So yes, it is a function. Okay, so now we know how to identify when we actually dealing with the function and when we're not. All right, so we can also have zeros of the function, right? So a zero of the function is when the f of x is intersecting the x-axis, right? So we can see it here, here, and here, right? For example, in this picture, in this graph, we have 3 solutions as of right now, right? Of course, we can have more, but how can we say for sure how many solutions we have? Well, the rule, right, the zeros of a function in general, in a function of y equal to f of x, we're going to find it the following way. It's going to be y equal to f of x, which is equal to 0. Right, so this equation, this specific equation, f of x being equal to 0, will provide us with the x values, which will be intersecting the x-axis. And of course, polynomials are much easier to solve because we can find the zeros of polynomials, but the higher we go in power, the more difficult it becomes. And of course, some of the nonlinear functions that we are going to be studying in the future lessons are also going to be not as easy to solve for. But let's take a look at the first example. right? Example 1, which we have done plenty of times already. So let's say that f of x is equal to 3x squared plus x minus 10. Okay, now we want to find the solutions, right? The x-intercepts. So we're going to say, okay, well, we have that f of x is equal to 0, right? So essentially we're letting y to be equal to 0 to find the x-intercepts. So we're going to have that 3x squared plus x minus 10 is equal to 0. Perfect. So what are we going to do? We are going to go ahead and factor this out, right? And we're going to be factoring out such that we're going to have something times something. We will have, let's see. Something plus something is going to be 1. Something times something is going to be negative 10. Okay, so it's going to be negative 10 and 1, right? Yeah, negative 10 and 1. So we're going to have 3x squared plus x minus, oh wait, no. So it's negative 10 and 1. If we add them together, that's not going to be the case. So let's actually do, let's see. Let's see here. Let's do, yeah, it's not 10. That's what was my mistake. So let's do, so it's not 10, it should be 30. That's why I'm not getting it. So negative 30. So then we're going to have two options. We have two options. We're going to have negative 5 and 6, right? So we're going to have, this one's going to be 6x minus 5x plus negative 10. So, okay, is equal to 0. So let's factor out. So we're going to have 3x times x plus 2. Okay, and then we're going to have minus 5x plus 2 is equal to 0. So we have 3x minus 5 times x plus 2 is equal to 0. And we've done those equations many times in the previous lessons. So we have that 3x minus 5 is equal to 0, or we will have that x plus 2 is equal to 0. So we will have that x is equal to 5 over 3, or we have that x is equal to negative 2. Right, so this is our solutions to this equation. So if we plug it in, we will get that our function has two zeros. And for polynomials, we will be learning the rule that the power of a polynomial will be the requirement to have the amount of roots we have, right? Even though sometimes we will have to clarify what kind of roots we are having, because it includes all of the roots, both real and complex. And if we're dealing only with real roots, that's going to be slightly different, because real roots are going to be sometimes, going to have less roots than we actually should have, because we're going to be multiples essentially of the roots. So, all right, and of course we can also have quadratic equations, and let's do one more example. One more example is going to be example 2. So example 2, which would be a fraction. So example 2 would say that f of x is equal to 2x minus 3 over x plus 5. And once again, we want to find that f of x is equal to 0. So we want to find the roots of the equation. So we're going to have 2x minus 3 over x plus 5 is equal to 0. But before we can multiply, we have to state that the denominator can never be equal to 0. So that means x plus 5 must not be equal to 0, but let's find out what kind of x is it. So it's going to be x not equal to negative 5, right? So x equal to negative 5, if we suddenly get a solution here, we may have to make sure that it's not the case here. So, okay, so x not allowed to be negative 5, which is fine. And what are we going to do here? We are going to say, okay, well, we can multiply both sides by x plus 5. So we're going to have 2x minus 3, x plus 5, so times 0 is going to be just 0. So we just have a simple equation where x is equal to 3 over 2. Okay, so we only have one solution here. So the graph f of x will intersect x-axis only once at x equal to 3/2. All right, perfect, perfect. And so, okay, we also have increasing and decreasing functions. Okay. And let's take a look at this. So a function can be increasing and it can be decreasing, right? Because different graphs, different functions will have different properties. So let's define all of them right now. So A function f is increasing on the interval when for any x1 and x2 in the interval, x1 will be always less than x2, and that would imply that f of x1 is less than f of x2. And I'm going to say this is number one example. So I will be giving examples for each. Then a function f is decreasing on the interval when for any x1 and x2 in the interval, for x1 being always less than x2, we have that f of x1 will always be greater than f of x2. This is called strictly increasing, right? In mathematics, this is strictly increasing. This is strictly decreasing, right? The reason why, because we have strict inequalities. And then a function is a constant on an interval when for any x1 and x2, the values, the f values of the functions are equal, right? They're always equal. So let's take a look at the following question. So we want to show that f of x, right? F of x is always greater than, well, x squared always essentially increasing, right? And the way we can do it is we can do it through, let's do this. Let's do for number 1, number 3. So for number 1, essentially, let's say f of x is equal to x squared, right? Okay, so we're going to say, well, we're going to have x1 being less than x2. And so what are we going to take a look at? We're going to take a look at the following. So f of x1 minus f of x2 must be less than 0, and we know that it's going to be true, right? Because, so if we plug in, we're going to have f of x1 squared minus x2 squared, right? We know that x2 is greater than x1, so their square, if we square both sides here, right, we can do that. So it's going to be x1, right? Essentially, we can multiply x1 and x2, and we know that they are going to be smaller than the other ones. So essentially, x1 minus x2 will be smaller than 0 because x1 square of x1 is still going to be less than the square of x2, right? So this one's still going to be less than x2 squared. All right, perfect. So this one was pretty trivial. Now let's say we want to find that, how about 1? So how about the following? For example 2, we will have, for the 2, we're going to have decreasing function. So let f of x to be 1 over x. So then we will have that, once again, x1 is less than x2. We have to make sure that f of x1 minus f of x2 will always be greater than 0. Right, so this one isn't as trivial in the sense of we have 1 over x1 minus 1 over x2, right? So it's equal to, our common denominator going to be x1 times x2. We're going to have x2 minus x1. Okay? And here, we know that x1 and x2, we're okay here, right? Because we are multiplying them together. So, but here we will have the following. So we will have 1 over x1 times x2, x2 minus x1. So regardless of the values of x1 and x2, right, let's say we can assume that they are both positive, right, just for simplicity. Both of them are greater than 0, then this is going to be greater than 0, and x2 minus x1 are always going to be greater than 0 because of this. Or if they are negative, then this multiplication is also going to be negative, so it will be positive regardless. So it also will be greater than 0, so the whole expression is greater than 0. So this function is decreasing, right? The previous one was increasing and increasing. And I'm just going to label it. Okay, and then a constant function, for example, right, 3, we're going to say that f of x is equal to 5. Right, for any x value, we're going to get 5, so there is no reason. So f of 1 is equal to 5, f of 2 is equal to 5, or for any x, it will always be 5, so that is a constant function, so we don't have to worry too much about it here. Okay, perfect, and so let's go ahead now and take a look at the next question. So we can also have to be able to find minimums and maximums. So essentially, a function can have the smallest value and the biggest value, right? And we can think about parabola, right? A parabola, or x squared, we will be able to find a smallest possible value, right? But we can't really quite find the biggest value unless we do something to the parabola, and we have to do some kind of different equation. But essentially, let's give a definition So a function value of f of a is a relative minimum of f when there exists an interval x1 to x2 that contains a such that for x between that x1 and x2, x will always be greater than any, the surrounding x will always be greater than or equal to that f of a. So f of a is the smallest one, right? And then function value of a is the relative maximum of f when where exists an interval from x1 to x2 containing a and such that, between that, the f of a will always be greater than the surrounding area, right? For parabola, of course, it's slightly easier to deal with because we are working with a parabola. We know that it for sure will have one either maximum or minimum, and the location, right? The location of the maximum or minimum of the parabola is located at its vertex, right? So if we have, we're just going to take a note here. For parabola, specifically y equal to ax squared plus bx plus c, we will have that the vertex, so it's the center of the parabola, right? Vertex. So I'm going to say center of parabola. The formula for it, for the x value, is going to be negative b over 2a, right? So if we have b, if we have a, we will be able to find the maximum or the minimum point. And the way it depends on the a value, right? If a is positive, we will have a minimum. If a is negative, we will have maximum, right? That's essentially how we can deal with it. Okay, and one more property. So of course, let's take a look at an example. That's a small example you can think of as y is equal to x squared, right? That's the easiest example. Of course, graphing will help, but here what we have to do, we always have to identify the vertex, right? And so we know how to graph this function, right? This function is going to be the parabola. And actually, let me do it more. Okay, like this. So this is our y equal to f of x. And we know that this point right here is 0. Our vertex is 0 because the b value here is 0, right? X vertex is equal to negative b over 2a. And in this case, b is equal to 0. So it's negative 0 over 2 times 1, which is equal to 0. So at x equal to 0, y is equal to 0. So y being equal to 0, we'll call it minimum. And in this case, this is not just a relative minimum. This is a global minimum because there is no smaller value present in this function, right? Sometimes for cubic polynomials, we might be able to find relative minimums, but for quadratic polynomials, oftentimes we will be only able to find the maximum. The maximum and the minimums, which are global. Okay, and now we can also talk about evenness and oddness of functions, right? So a lot of functions in mathematics have such properties that a function can be even and a function can be odd. Right, and of course, a lot of geometric functions or trigonometric functions have that properties. And we can take a look at this. So a function is even when for each x in the domain, f of negative x is equal to f of x. That's even function. And then the odd function, when for each x in the domain, f of negative x is equal to negative fx. So for this is number 1, this is number 2. Okay, so for number 1, let's go ahead and have an example. So f of x is equal to, let's say we're gonna have x cubed plus x. Okay, so we're gonna have that. So if we say, okay, well, let's check f of negative x is gonna be negative x cubed plus negative x. So that's equal to negative x cubed minus x. So we're gonna factor out negative 1 times x cubed plus x, which is our f of x. So we have negative f of x. So boom, this is odd function, right? And that's actually number 1 as a example number 1. That's what I meant, not for number 1, but we define it as the odd function. So example, I will say 2, right? And then example 3, we'll have f of x to be equal to x to the fourth plus x squared plus, let's just say that. So we're going to have f of negative x is equal to negative x to the fourth plus negative x squared. So we know negative 1 to the fourth is just 1, so we're going to have x to the fourth plus x squared, which is just f of x. This function is indeed even. Okay, and we can do that with a lot of functions, and we can check it, but sometimes the function can be neither, right? Sometimes the function can be neither, and an example of such function is, so I'm going to take example 4, which is going to be neither, so f of x is equal to x to the fourth plus x cubed. Right here, f of negative x is going to be negative x to the fourth plus negative x cubed, which is equal to x to the fourth minus x cubed, which is nothing. We cannot do anything to it to actually factor out or do, so it would be neither. All right, perfect. So, all right, now let's go ahead and talk about some of the parent functions. So we know, what do we learn so far? We learned so far linear functions, square functions. We slightly talk a little bit about the cubics, the square roots, right? We know how to solve the square roots, but now let's have more of a summary of some of the functions and some of the graphs, right? So let's go ahead and talk about the cubic equation, right? So cubic equation is when we have the following. So f of x, x cubed, right? This is the cubic equation. So this would be the graph of the cubic equation. So we have the domain to be all real numbers, range is all real numbers. The function is odd, as we just checked it, right? And the graph has one intercept at 0, 0, and the graph is increasing on the interval from negative infinity to positive infinity. So we can also check that by the previous definitions. And it's symmetric with respect to the origin, right? To the point 0, 0. Okay, now so we know a little bit about it. We solved some problems related to it. Now let's take a look at a square root, right? The square root function. So the square root is, there's a square root, is going to be square root of x, or it's the same thing, remember, as x to the power of 1/2. So the domain of the function is the all non-negative real numbers. The range of the function is set of all non-negative real numbers. The graph has an intercept at 0, 0. That's the only intercept we have. And the graph is increasing on the interval from 0 to infinity. Right here we have positive infinity, and here we have positive infinity. Okay, perfect. Now, one more equation that we talked about, right, which is 1 over x. We know that this equation is odd. And notice that, we cannot have oddness in the square root because we cannot take a square root of a negative number. Right, this is one of the properties as well. So it's neither in this case. So, okay. And the last equation is x, 1 over x. So we found out that it's actually odd function, right? And it's decreasing, right? Odd because x is odd, right? X is odd, so we know that it's odd. And we know that it's a decreasing function because we checked that. So the domain of the function is from negative infinity to 0 and from 0 to positive infinity. The range of function is from negative infinity to 0 and 0 to positive infinity. 0 and 0 is not a point. The function is odd, doesn't have any intercept, and is decreasing from negative infinity to 0 and from 0 to positive infinity. So it's always a decreasing function, right? It's a decreasing function, and it's symmetric with respect to the origin once again. So you see, if we have a function here and it's symmetric with respect to the origin, it will appear in the opposite quadrant. So if it's a quadrant 1, we're going to be in quadrant 3, right? That's what means to have a symmetry about the origin. All right, and then of course we might also talk a little bit about some of the special functions that are present in algebra. So one of those functions are going to be called piecewise functions and step functions. So floor functions and the ceiling functions. So let's go ahead and define the piecewise function. So a piecewise function, we can write it as f of x, and it's going to have essentially pieces. So it's going to have f of 1 of x, f of 2 of x, dot, 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 all the way to as many f of n of x we want to have. And it's going to be for some x belong to the domain D1, and then for x belonging to domain D2, right? We can have multiple domains. And then for x belonging to the domain Dn, right? This is going to be the piecewise function. And of course, an example of such function would be f of x to be equal to x minus 1, right, for x less than or equal to 1, and x plus 1 for x greater than 1, right? That would be an example of such, right? That would be two lines. We've already be shifted where there's going to be a jump between them, essentially, if we graph them. But we know that 1 is a cutoff point, but it's going to be, the values are going to be present, so that is a perfectly fine function. Okay, and then we can also talk about floor function, right? So a floor function, the meaning of that function is essentially we are decreasing the value as we plug in the x value here. So an example of such, so the notation would be x, right? So if we have a value, let's say, of 3.9, and we're applying a floor function to it, it's going to be 3, right? A floor function to pi, where pi is 3.14, so it would become 3. Okay, and this is a floor function, and then we have a ceiling function. A ceiling function. So a ceiling function is similar notation to the floor function, just like this. So here we would have, I'll say f of x. F of x. So here we would have similar idea as a floor, but if we have ceiling of 3.9, it would become 4. A ceiling of pi, it would become 4 as well. So, etc. And then for the negative numbers, let's say the floor of negative 2.1, that would become negative 3. And the ceiling of negative 2.1, that would become a value negative 2. Right? So it's slightly shifted here, right? In the sense of the numberings. So, okay. Now, what we're going to do is we're also going to define one more piece, right? Function number 4, that's going to be the fractional part. Fractional function, which is related to the floor and ceiling, but the way it's defined is defining the following. So the fractional function, we put it at squiggly brackets, is equal to, so it's the value x minus the floor of x, right? And essentially that is whatever is left over from the original value of x, because when we are applying a floor or a ceiling function, we are going to be losing that value. Okay, perfect. So now that's essentially like a quick overview of the function, right? And here we would have an example, right? Of course, we can graph them. We can graph the floor functions. It's just going to be straight lines for all of them, right? You can imagine the following shape, right? We're going to have this shape. So for the floor function, 1, 2, 4, 1, 2, 4 as you go. So this is going to be 0. Then for the values 2, right? Everything between 1 and 2 is going to be here, right? Then everything between here and here, so this is value 2, so it's going to be right here, right? And it's going to be stepping up as we go, stepping out in one direction, stepping out in the other direction. So always the end of it is going to be open, meanwhile this end is going to be closed. And similar for the ceiling function. For the actually fractional function, right? For the fractional part of a function, we will have it as the following. It's going to be slightly different. So this is going to be this function. So it's going to be, say, 1, 2, 1, 2, 3, 4, negative 1, negative 2. So it's going to be like this. Like this. This is a fractional part. Okay, perfect. Now, let's go ahead and talk about some of the transformations of the function, right? We can be transforming functions. So transformation essentially is rotation and translation of the functions. with transformation. Let's talk about specifically. So if we have a positive real number, let's call it a c, then we can have the vertical and horizontal shifts in the graph of y equal to f of x so the vertical shift is units up, so we're going to have the new h of x, which is going to be f of x plus that constant c. That's when we want to move it upwards. Then vertical shift c, units down, we're going to subtract the c units. And then if we want to have horizontal shift, we're going to include it into the function as x, right? So an example of that, so if we say we have x squared as f of x, then our new h of x is going to be x squared plus c, x squared minus c. Then we're going to have x minus c squared, x plus c squared, right? There's a difference between them too. So it's important to keep that in mind, especially for the polynomials. The students oftentimes make mistakes in polynomials, right? So let's take a look at a book example here. So we're going to have the following two figures. We have f of x, right? We want to move it downwards, f of x cubed, right? We already talked about a few of those problems. So f of x cubed, if we want to move it down, subtracted 1. If we want to move it to the side 2 units and upwards, so to the side 2 units to the left. So now this point 0 moved here because we added 2 units to the x to move it left and added 1 unit upwards to move it up. Okay, so that would be a great example for it. And of course, we can also have reflections, right? Reflections of a function is actually relates to the properties of functions being odd and even, right? But essentially, we have in the coordinate axis of the graph, we can say that reflection in the x-axis, we would have to forcefully add the negative sign to it, right? Especially if the function is already even, that would work perfectly fine. And reflection in the y-axis is we are inputting it inside of the function. So we can imagine a function, a quadratic function, right? Quadratic function is an even function. So perfect graph for this function would be as following, right? This is f of x, and we decided to do the reflection, so we're going to have negative x squared. All right, perfect. And of course, we can have scaling, right? So scaling and multiplication as scaling would have stretching essentially the graph, right? If we would have multiplied the graphs or subtract the graphs. So the perfect example would be, let me call it as stretching here. So stretching graph. So we can stretch graphs, we can compress graphs based on the points. We can, have a vertical shrink or horizontal shrink. So essentially, we can have following pictures we can imagine, right? And a good representation of that you can try to play around with at Desmos. You can have it as, so 3 times absolute value of x. This is how the absolute value would look like as a v, right? Letter v. But now if we multiply by 3, it becomes very sharp, right, compared to this one. And then what do? We can say, well, let's say if it's not 3, let's do it as 1/3, right? 1/3 of the original graph. So then we would have something like this, right? It would change. It would change, and now it becomes less sharp. It becomes more dual, right? So essentially, we stretched it along the x-axis. Here, we kind of compressed it. And of course, we can do it to any functions here. So you can definitely play around with it. And what we can do, we can also have the compositions of functions. So of course, we haven't yet seen any of that, but we can do some of it already by subtracting and adding functions together, right? But we haven't yet done any specific compositions of functions. So here is some of the simple compositions that we can do right now, right? If we have two functions, f and g, we can add them as a sum, right? We can just directly add them, and it's going to be some kind of new function. We can have a difference of them. We can multiply them, and we can divide by them as long as the denominator is not equal to 0, right? This is something basic that we've done, and we can do, right? As soon as we defined 2 functions, we can go ahead and do that. Now, The more important part is the composition, right? Composition is when we have f of a g of x function instead of just a regular addition and subtraction and multiplication. So here, let's take a look from the definition and from the definition from the book that provided by the book. So let's take a look at this example. We have the following, right? We have that the definition of composition of two functions. So the composition of function f is a function g. This is the two notation. We can notate it with the open circle, or we can say that it's f of g of x. And essentially, we have the domain of g and the domain of f, and now we have f of g, right? So that's how it works essentially. So the domain of f in g is the set of all x in the domain of g such that x of g is in the domain of f, right? This is a figure example of it. So let's say we have something example, right? Example 2.1, let's say. So we have f of x is equal to x plus 2. G of x is equal to 4 minus x squared. Okay, so if we do f of g of x, right, we simply have f of g of x. So we're going to have f of 4 minus x squared. So that's going to be 4 minus x squared plus 2. That's going to be minus x squared plus 6. Right, let's say we have this as part A. Part B, if we have g of f of x, composition of g of x, so it's going to be g of f of x, right, and that's going to be g of x plus 2, which is equal to 4 minus x plus 2 squared. Right, and of course, we can simplify this, and I believe, yeah, we should get negative x squared minus 4x. Okay, and of course, we can evaluate at different x's, and it's going to be different values of it. All right, so that was a basic introduction to the composition. Next time, we'll do some more problems on composition, and we will be continuing with our algebra course. Thank you, students, and see you next time.